Okay, so as I said, we're in the middle of chapter 11, and chapter 11 is all about the challenges of doing approximation when we want to consider off-policy learning. So with off-policy learning, there's some behavior policy, which is could be different from a target policy we want to calculate the values for. And in the case of approximation, we are not free to just save a value for every state like we would like. So in this was the last, I think, example we went over before we finished last week. But in this example, this is a very simple problem where there are only two states in the problem. So normally, if we were to solve this, we would just compute the exact value of this state, and that would be the answer. But as sort of, this is a toy example of what we do in approximation. And what this diagram means is that there's some weight value W, and we're going to use this weight value W to approximate the solution, assuming we can't have an exact one. And that means our approximation value for this state will be W, and for this state will be 2W. And for this particular problem, the rewards are always for 0. The actual exact solution is W equals 0. It doesn't matter that there's a different constant multiplying this because the exact value is 0. But in general, this relationship between the states is sort of imposing some ratio or grouping the states somehow. When we did linear approximation in general, these sort of values of each state would be represented by the feature vector in general. So like in this case, the feature vector for this state is just 1, and for this state is 2, which is why there's a difference between the values. But this relationship is enforced by however you represent the states by the feature vectors, right? So like this value in the approximation must always be double whatever this value is. So we already had to deal with that and those constraints earlier, but in the in doing off-policy training, this counterexample is doing a calculation where all of the state, like both states, are just weighted equally in terms of the error. And this is sort of like this temporal difference error here, which is already actually a different objective than what was considered before. But this example tries to calculate what the weight update would be if we try to minimize this on every step of some training process. And I had, it's not like what ends up being calculated here is something which we went over where there's some condition under which this update diverges, where the values just grow over time. And I had also done this calculation here where the exact solution is both values are 0. And then if you try to calculate the TD fixed point here, you end up getting this correct solution. Oh, sorry, this was doing, okay, no, forget this part. If you ignore the on-policy distribution as is done here, you end up with this divergence condition, which this just fleshes out the algebra, which is missing from the book. And then this only diverges when this value is greater than 1, this value multiplying omega. So even in this case, there are cases where the weights won't diverge, and we found it was for as long as if epsilon is greater than 1/4 in this case, and the higher epsilon, it just means this goes to the terminal state. There's a higher probability of this going to the terminal state the higher epsilon is. Then the gamma for which this diverges is greater than 1. And since gamma is always less than 1, this will never diverge, and there's no problem. And if you instead do this like properly, where you're supposed to consider the distribution of how states are visited, like in this case, the reason why the off policy update fails here, or diverges, it doesn't compute the correct values, because really like this objective function should consider the probability of being in each state. And this state, for any value of epsilon, is going to, be revisited more often than this state. So if you account for that, and here I'm calculating, this is showing the on-policy distribution for both states, and in the extreme case of gamma is equal to 1, or sorry, of epsilon equal to 1, then the visit, the state probabilities are exactly the same. And in that case, obviously, if epsilon's 1, it is greater than 1/4 in this case, and we never have any divergence problem. And actually, this assumption of both states being weighted equally is exactly correct for epsilon equal to 1. But even for all the values of epsilon, if you account for this and do the same calculation, you end up that the gamma that is problematic for this is just always greater than 1. So this never diverges, and you always get the correct convergence property. So again, like this is like an off-policy example here, because this equation that was written down is ignoring the on-policy distribution, and it's just a warning that you can't actually do that. I mean, if you do that, not only will you get the incorrect answer, but you may even get some update process that just diverges to infinity. So the answer is just nonsensical. So I've done this, and I had, if you look at the notes, this example, I had, expounded on it more. I also calculated the TD fix point up here, and I think I calculated it. If you compute the TD fix point, which again, like with the TD fix point, you get a different update for each state. So like there is some weight update that you get for transitioning out of state 1, and then another update for state 2. And this, again, like we're just doing this with these samples, and we don't actually consider like the distribution here, because I'm just considering the update from a single sample. But you can see here for the TD fix point that this update like converges, or like the actual updated value is 0 when the weight itself is 0. And that makes sense because we had already shown earlier that the TD fix point was within some bound of the value error for this. And we know that if we set W equal to 0, the value error of this is 0. So like we can solve this exactly by just having W equal to 0. So we would expect, if we were to like solve this with TD, like TD learning sampling, that we would end up with the exact solution here. I think in this, let's see if I show solving this. Yeah, so this is showing on policy like TD0, this learning algorithm that in all these charts, different charts I made. Let's look at so this is a case where this update, these off policy updates are diverging, and if we consider the on policy TD0, it correctly has the weights converging to 0. Yeah. Okay. So that was this example. Then, the other like lingering problem from before was we had also looked at this Bard's counterexample problem where, there's actually enough parameters to solve this problem. Exactly. There's 8 parameters and 7 states. And we had seen that if we do the same kind of update, off-policy update, where we ignore the state distribution, then we also get diverging values. And then when we do Q learning, so like I have an implementation here of Q learning for this example. And when you do Q learning, you are doing like off policy learning, but it's not exactly like this. Like this is an extreme case where they're just weighting all the states equally. With Q learning, remember, like we're doing the expected update, or we're following like the epsilon greedy policy, but then the target policy is just the greedy policy. So there is this difference by a factor of epsilon, and you could crank up epsilon to be very large, in which case you would just have the random policy. So with Q-learning, you can sort of make the behavior policy as far off from the target policy as you want. And in this example, they say, okay, like solve this with Q-learning. Now, it's kind of a weird problem because again, like in this case, all the rewards are 0. So all the policies have the same expected reward. Like there's no, like Q-learning could in theory find like any policy would still match the optimal policy, because in this case, all policies are equal. So it's already kind of a strange problem where there's no optimum. But like we saw, if we just try to learn the values with this off policy learning, then we get this diverging behavior. And it seems to just diverge out to infinity. Now, I had solved this earlier with Q-learning, and these are just some different charts. So on the left chart is if you just do like semi-gradient Sarsa, which is the on-policy method where I have some value of epsilon. And in this case, this is showing the weight values over time. And this is showing the value, I think, of a particular state, or perhaps it's showing the value of one of these states. And the point is that, you would expect if this converges, it should learn that the state value is 0. And it's not exactly 0, but you can see that like it sort of dips down and eventually it is like, there's some variance, but it is converging to the 0 line. And the weights aren't diverging at all. If you do this with Q-learning, you see at first the same divergent behavior that you get here, but then there's this point where it actually becomes okay again, and it starts converging. Now, if you would just stop this learning process at like 4,000 steps, then it would look like the weights are diverging. And sorry, actually, I think what this final thing is showing is which action is favored. So, because in both of these cases, I'm learning state action value approximations. So the Q-learning, like in addition, in this case, these weights are just representing the state values. But with Q-learning or with Sarsa, we have sort of like 2 sets of these estimates. We have all these estimates for the solid action, and then the same set of estimates for the dashed action. And whenever you're doing Sarsa or Q-learning, this line is showing like which action is favored. So this is saying like action 2, this is like the value of action 1 minus the value of action 2. So here we can see early on in the training process, action 2 is favored, and then over time, action 1 becomes favored later on. And I think this is actually showing all the state values. And if I were to increase this, let's see, so this is doing it for 10,000 steps. So I think if I increase this to more, it doesn't take too long to run. You can see that actually all the state values it's taking a long time, but they are converging to 0 for both Sarsa and Q-learning. But I ended up shortening this so that you could actually see what's happening early in the process. You can see with Q-learning, you have the same phenomenon where at first one action is favored, and then this transition point happens, and then these weights that were originally diverging then start converging. And I think there's something where even if you're doing off-policy learning, if the 2 policies are close enough together, like same with this earlier counterexample, or this later one, where we saw like if epsilon was large enough so that like the 2 policies, the target and behavior, were close enough, then you get rid of that divergent behavior. And in this case, they're sort of as far different as they could be. which I had made a chart here of like, you know, this is the state distribution under the behavior policy and the target policy for this. So this was contrived so that these distributions were as different as possible. Now, when you do Q-learning, there might be an initial point when that's still the case, but because all of like any policy is optimal, exactly which action is favored, and like in theory, even if you're doing Q-learning, like the epsilon greedy policy and greedy policy can get close to each other because whichever action is favored between the states can just flip back and forth as the learning is happening, and it doesn't actually affect the final answer because ultimately all of these state values and all the state action values should converge to zero. So I think like even though you see some amount of divergence here, I think sort of eventually you get saved by the flexibility of the policy. So I at least wasn't able to see a case where, I mean, even here setting epsilon to 0.99, which makes the behavior policy under Q learning completely random, it still didn't seem to cause this divergence to last forever. So I don't know if anyone else looked at this problem, but I'm hoping that the point of this exercise is that you can see that the weights like do diverge for some period of time. And I guess if it was a very complicated problem where you could really only train it for this limited number of steps, you would see this maybe and just give up, or because you would hope you wouldn't expect it to eventually converge. But it seems like eventually it does get corrected. Whereas, yeah, like the same counterexample, like just like in the book, so showing if you do this sort of training and you go forward in time, I mean, this is only showing for 10,000 steps, but yeah, I think if I extend this to more steps, because I think I tried this earlier, and you don't actually see, yeah, like the weights, at least in off policy training, they just continue to diverge, and they get to basically infinite value and in the numerical precision before they have a chance to converge, if they ever converge. I'm not sure, and I think and the claim is that this should happen even if no matter what the learning rate is, and I believe that is the case. With on policy training, you could also make the weights diverge if the learning rate is too high, but that's not a problem with the algorithm. That's just, I mean, that can always happen when you're doing gradient descent. If the learning rate is too high, you can get divergence. Here, I'll set this back here. So yeah, like this seems to be like these specific cases of divergence seem to be, they only happen if you have a big enough difference between the target and behavior policy. But yeah, even if that's not the case, you still like the value, even if they don't diverge, the values could end up being incorrect just because you're not actually computing the right objective if you're not visiting the states with the right frequency. So yeah, I don't really have any more to say about at least this example or exercise. But so I'll just move on to the next section unless if there's any questions about this. Yeah, and the divergence sort of being a temporary effect. Yeah, that was this exercise. If anyone else is going to try it out. Okay, so I guess I should move on to the next section, right? Is that right? Okay, so the rest of the chapter goes into some more detail about all these cases in which, you know, we get problematic behavior, whether it is, diverging weights or just wrong values. I mean, it turns out a lot of things that can go wrong if you're not very careful. And the claim is that there's this deadly triad where if all, three of these things are present in the learning process that you're doing, then you can get major problems with the convergence of whatever the approximation is. So, function approximation is what we've been talking about in the entire section 2 of this book. And that's just the fact that we have some weights or some, we are not free to just have a separate value for every state. I mean, that's common across all forms of function approximation, as opposed to where we don't have approximation in the tabular case where we can have a distinct value for every state. So that's what this means. We have there is some relationship between the state values that is artificially imposed on the problem. So that's what happens with function approximation. Now, bootstrapping is where, we are going to, in general, for these problems, we're going to sample data from the problem. And if we don't want to use bootstrapping, then we need to be able to collect a sample of the value, an unbiased sample of the state value. And the only way to do that without bootstrapping is with Monte Carlo sampling, where we look at the rewards under a policy out to termination. And unfortunately, if we have a continuing problem where we don't have any terminal states, then the only way to get samples of the values is with bootstrapping, where we have to actually use our function approximation or, our estimate of some other state values, right? So this we already saw. If we do bootstrapping with approximation, we already have had a problem with the value error in that we had this semi-gradient method, and the point we're converging to is not actually the objective that we wanted, that the minimum value error that we had defined in chapter, I think it was chapter 9. Oh yeah, here. So in chapter 9, right, like we had said, if we're doing approximation, we're trying to minimize the value error. And the value error, right, is like there is some unknown true state value that we're going to sample. And if we do Monte Carlo sampling, we can replace this with G, let's say. But in bootstrapping, we can't do that. And then, right, we had this issue with where, we were using this value to replace our sample of V. And the problem with this is that now our estimate, or like our target value estimate, actually also depends on the parameters. So this ends up causing a situation where we end up converging to something different. This was back in chapter 9. We have this example where we have this very simple problem. And if you do the training with Monte Carlo estimation, you get, this blue line, which is the correct value error. And if we do it with TD zero estimation, we just get this other solution. And this is totally converged, or actually in this case, it's not converged, but there's another chart, I think, where I have the exact solution. But you just end up getting a different answer. And the TD fixed point could be very far away from that true answer. Luckily, there is some theoretical bound that keeps it close, but we don't, like, that bound could in theory be very, very far away. But at least, it's constrained somehow. Like practically it often is very close, but we don't know. So, we already had, even with on policy training, that's already a problem with bootstrapping. And then if we then add off-policy training to the mix, then in addition to the values not being entirely accurate maybe to what we want, we also have cases where it can just fail completely and the weights can diverge. So, from what I had just said, if we have a problem where, we have to use approximation, which are all the problems we're considering now, we're assuming that, the state space is too big. And then often we do have continuing problems, in which case, we do have to use bootstrapping because we can't even do Monte Carlo sampling. Then, we can't, we shouldn't really do off-policy training in those cases. Or, we could if we treat it very carefully. Later on we'll see there is a method that actually with only linear approximation, there's a method that can avoid some of these problems. But otherwise, if we just proceed with off-policy training as we've tried so far, we can see that none of the algorithms that we have can handle it unless you properly account for the distribution of states being visited. So in the book they mention so now if you have an episodic problem, you could dispense with bootstrapping, and that would help somewhat, because if you're back to doing Monte Carlo sampling, you can collect these unbiased estimates of the true value, and then there's other things that we can do. But in general, we're not going to be able to do that. Q-learning technically is an off-policy method, but like I said before, if the behavior policy is close enough to the target policy, then it might be okay. So you actually have cases where you do have this deadly triad present, but the off-policy training piece is just, it's not extreme enough to cause all the bad behavior that we saw, but it could still cause problems potentially. But all this is kind of abstract, and the next section tries to create this sort of visual conceptual aid to exactly what is happening when we use these different algorithms. So I think we can first look at just what it says in the chapter, and then I'm going to show a slightly different version of it that uses it actually kind of simplifies the diagram a bit, but shows it as sort of a concrete example. So the idea in the book is that we're going to visualize all the different objectives and training algorithms that we could use in this geometrical space. But to make things easier, we're just going to consider a problem where there are 3 states. Okay, so the reason why we're doing 3 states is because this is we have 3D geometry. And then because we're considering approximation, we have fewer weights than we have states. Right? So we have to somehow represent the values of all 3 states with just 2 weight vectors. And how that representation works will depend on the feature vectors of the states. There's an infinite number of possibilities, but one possibility that you could do is you could have just the value of state 1 is W1, and then state 2 and 3 are just shared by W2. That would be a very simple one, but in general, each state could be a different linear combination of W1 and W2. Okay, does that make sense? I mean, this is just the same as all the linear approximation that we had looked at before, where I don't know if I have it clear example right now, but when we do linear approximation, all of the have these features. If I can find the formula, but all the state values are just oh, here. Yeah. So with the linear methods, all the state values are just the inner product of whatever the current weight vector is and the feature vector, right? And these feature vectors should just tell you, for a given state, how much does the value depend on each of the weights. Okay, so then the idea is that, given that we only have two weight vectors here, but, like the true value function lives in this 3D space, that the approximation, whatever the, which is defined by whatever the feature vectors are, take this slice out of the true space of value functions, and the only value functions that we can represent with this form of approximation are, lie in this plane, which is in the larger 3D space. So we have the plane, and then there is some point in the full 3D space, which is the correct, like the true value function, right? So that's like this point for the three states where, if you imagine that there's some other axis in this diagram which isn't shown, which is the value of each state, of each of the three states in the 3D space. And then the objective that we had defined is like what our ideal objective is some point in the plane which is closest to this true value function here, right? And like however the plane is drawn, this point that minimizes that distance is going to be, perpendicular to the plane. And there is some, if we end up projecting this point down to the plane, we can find out what these two parameters are that minimize the value error. And then what's also shown here is the fact that, if we have some arbitrary approximation, then in the plane, right, that's going to be some arbitrary point in the plane. And then when we apply the Bellman operator to this, and the Bellman operator, again, we hadn't really looked at it as an operator before. We had looked at it in terms of what happens at each state. But this is taking, like, remember, when we have the Bellman operator on a state, is that we look at whatever, it tells us what the state value should be versus what it is. So we can always apply this operator to any state, and it just ends up taking the state value or in this case, like it does in general depend on all the state values, but this is this like look ahead, right, bootstrap function where it's saying like the value of state S should be this sum. These are just all the probabilities of all the transitions that could happen, but of the immediate reward plus the discount rate times the value of the state that you end up in. So you can look at, all of the state estimates that you have. And in this case, if we're in the plane of approximation, we have, like this is also a point in the 3D space. And then this is showing how the values get updated when we apply the Bellman operator. And then when we have the true value function, and this is what we did before with like value iteration or, policy estimation with the Bellman equation, we arrive at this point where the Bellman operator doesn't change the value at all, right? And that's so, right? This like true value function is a fixed point of the Bellman operator. But you can see that in order to do this properly, we can't have any constraints on the state values. They have to be anything. And we've already imposed this constraint in the plane by the approximation that we are doing. So here's the value error. So we can't actually, follow this like what we would normally do with policy evaluation because we go outside of the plane. Now, there is some distance for any of these points. There is some distance down to the plane for any point. And, this is showing like if you apply the Bellman operator once, you in general have some point outside of the plane. And then you could look down and see like, okay, well, how far away is this from the point that we started out with? And like, if we move this point around the plane, this Bellman error vector will change. And it's not shown here like how you arrive at that, but the idea behind this point, like, is that if you took this point and you applied this Bellman operator, the Bellman error vector, like this arrow at this point, would be the shortest possible that it could be. We know it can only be zero up at this point outside of the plane, but there should be some point in the plane where this is minimized. And that is going to be, some other point. Like it's a distinct point from this point of the minimum value error. And then there is this other point, which is that, if you project this Bellman error vector into the plane and you compare it to the starting point, this line is called the projected Bellman error. And it turns out, which there's not like a general proof of this in the book, but I do have, you can demonstrate it with some specific examples, that there is a point in the plane where this projected Bellman error is zero. And that is actually a point where, like, at this point, the Bellman operator will be perpendicular to the plane. I mean, that's obvious from the diagram that if the projected Bellman error is zero, then the Bellman like error vector itself is perpendicular to the plane. But that is also not necessarily the same. Like, this point is the one where the Bellman error vector is the minimum length. But the minimum length, like, that doesn't mean that it's perpendicular. So the difference between this point and this point is, this is the point where this is the minimum length, whereas this is the point where the Bellman error vector, no matter how long it is perpendicular to the plane, which is also going to depend on how we represent the states. Like, in this example, they don't even mention what the feature vectors are. But if you imagine, like this answer, like all these points will actually depend on how the feature vectors are defined. And then this is a different thing, which, yeah, I think it's probably better. Yeah, I think it will be more clear to see what's happening here with the next diagram I have, which is actually, I made a diagram of this, but it's in 2D space instead of 3D to make it a little easier to see. But I know that this whole thing is like a little abstract if you don't work it out. But are there any questions about this before I move on to the simplified version of this? Okay, I'm going to skip ahead a bit to show this other MDP, because to do this next part, I was actually going to, so here, this is an MDP, this one on the right, where you have two states, and this is a continuing problem, right? It just loops forever. And each of these arrows is just 50% probability. So for the left state, you can either transition back into it or to the right. And they both have a reward of zero. And then this right state you can either transition back into it or to the left or to state one, and there's a reward of two. Okay, so you can solve this problem exactly, right? It has two states, and here I am showing if you use the Bellman equations, you can solve this problem exactly. So here's the equation for V1 and the equation for V2, and you end up with this expression for V1 and V2, where V1 is going to depend on the discount rate, right? So it's gamma over 1 minus gamma. If you set gamma equal to 0, then V1 is 0, but otherwise, it's some function of gamma. And then V2 is just always 2 plus V1, which is kind of obvious from how this diagram is set up. So this is just showing, this is showing the difference between V1 and V2 across all the different discount rates. And there's always this difference of 2 between them. So that's the exact solution to this problem. Now, similar to what, if you think back to that 3D diagram, this one, I'm going to, instead of having 3 states and then 2 parameters, for this problem, there's only 2 states and 1 parameter. So everything is like 1 dimension simpler. But I'm going to now consider this approximation kind of like the previous counterexample, where the value of state 1 is equal to W, and the value of state 2 is CW, where C could be, any constant here. I'm considering it usually to be a positive constant. So C could be 1, right? But it could also be, 1/2 or something different. But this relationship between C1 and C2, what ends up happening, so here's this diagram worked out. So what this diagram is showing is all this whole plane of this diagram represents all the possible value functions for this problem. And because there's all the values for V1 and V2. Okay. Now, the true value function is this point here, right? And it depends on gamma. So I'll show here, if I change gamma, you can see this point moving, right? This true value point. And it's just moving, but you still have this relationship where V2 is always twice, or V1 plus 2. So I'll make it back to 0.8. So here, right, V1 is 4 and V2 is 6, right? So it's 2 more. Okay, fine. Then this light blue line is all the space of approximate value functions that are imposed by this relationship, right? And this blue line depends on the linear constant here, right? But if we have this form of approximation, right, these are the only possible approximate value functions that we can have. You can see, so I'll move this line around. So this is just making the slope more shallow. In the extreme case, like if it's 0, then V2, is always 0. And then if I make it like greater than 1, then yeah, it has a more extreme slope. So if you were to compare, like instead of the weights and the feature vectors defining this plane in the 3D space, now it's just a line, which is a slice through the 2D space of all of the value functions. Okay, we're still, this is the problem, except, here, imagine there's just a CW here, where in this example in the book, C is just 1. Okay, so now here, if I set C to 1, it turns out it makes the problem a lot. Or wait, sorry, that is not the linear constant. I set it to 1. Okay, so this is showing, okay, so what this diagram is showing is like, right, this is the space of all of the possible approximation functions, right? But I have this other point, this evaluation weight. So this is saying, like, let's say I set W equal to 6.5. Or here, I'll make it a little higher, like 7. Okay, so you can see on the diagram here, W is 7. So if W is 7, right, this is the approximation that we have, 7, 7. right? Because I have C is 1, so they're both equal. And all these other points are showing these other errors that we could evaluate for this. So this purple, or this, purple point up here is showing, I'll go back to this diagram, this Bellman error vector. This dotted line is the Bellman error vector. But this point is the Bellman operator on this. So it's saying if you took this approximation here, 7, 7, and you apply the Bellman operator, you would get this point here, which is outside of the line. Then this dotted line is showing that being projected back onto the line. And then this orange line here is showing the value error, right? Because this is the distance from the approximation value to the true value. So normally, what we're trying to minimize here, the original thing we were trying to minimize was the value error. And you can probably see already just from this diagram, like, first of all, like the value error is going to be the point on this line where the vector pointing to the true value is perpendicular to the line. And because C is 1, that is going to happen, well, we can actually, I will move the evaluation weight. You can see as I move this, all these other things are updating. And there, right, is some point here where this orange line is perpendicular. And this is the point of minimum value error. It turns out as you move this, you can also see the Bellman operator point. And when C is 1, it turns out that all of these things actually line up with each other. So the point that minimizes the Bellman error is the same point that minimizes the value error. And that is, and also the TD fixed point, right? Because here the Bellman operator is also, like the Bellman error vector is perpendicular to the approximation line. So the projected Bellman error is also 0, and everything agrees, and all the methods agree, and it's fine. The problem is, right, this depended on C being 1. If I change the linear constant now, so let's say I make it, like 0.5 or something. So now, I've changed the slope of this line. So now the point of minimum value error is going to be different, right? I can shift this up. Oh, sorry. The value error actually is this, the orange line here. So, sorry, this is cut off a little bit. Okay, I can't read exactly the title is, but also there are this other graph here. And what this graph is showing is all of these curves are showing the different error functions across all of the possible weights that we could pick. So here, I'll show, so the minimum value error occurs at 5.4, which is actually the weight I have selected here. And this is the curve of showing the value error for all of the different evaluation weights. But now, because C is not 1 anymore, so let's consider the Bellman error instead. So this is the curve for the Bellman error, and sorry, actually, I don't believe it's a, no, 5.4 is just this point I have, but it'll make it easier if I just show these curves without any other point. So you can see where the value error is minimized is somewhere around here, right? But the Bellman error curve has this minimum, very far away from it. It's not even close. And then here's the projected Bellman error line. And where this error is 0 is going to be the TD fixed point we already mentioned. You can see again, in general, it is not the same as the value error, but it is closer to the value error than this point of minimum Bellman error, which this is for one particular example, but we'll see that with other examples, this seems to be a consistent pattern that like the Bellman error doesn't have any, if you solve it, it doesn't have any clear relationship to the minimum value error, which is a problem and a reason why it's considered a bad idea to use compared to these other things. The other nice thing about the projected Bellman error, which here I'll show if I move this evaluation weight, remember the projected Bellman error is the distance here from this green point to, you know, this dotted line here, right? Because this dotted line is showing the Bellman operator projected down to the line. And you can see as I move this over, the projected Bellman error is shrinking. And eventually it will become 0. But you can see as I move this, the value error is growing, right? So these don't match up. And these would only match up in that case where C equals 1, like I showed before. And then I have to go even further to the left to get to a point where C, you can see now this Bellman line, this light orange line, is continuing to shrink even if I go more to the left. You can see this is actually minimized when W is a negative value, which is, you know, really a problem because right in this problem that I set up, the rewards are 0 and 2, right? Like there's not actually a single like negative reward in the problem. So, but depending on what the value of C is, like here I'll make it even smaller, and it does end up shifting. And actually, there's this other error to the TD error, but you know, you wouldn't expect any approximate solution to have a negative value of W, like, and it's this quirk of how the error is calculated. But you could see it might be a bad idea to use this because if you look at this other method, like even this method, which, you know, obviously the solution is not matching the minimum value error, but at least it's a positive number, right? It's not going negative. And we can see that the same thing if I make linear constant greater than 1. Now it sort of shifts all these curves around, but we can see that the point where the value error is minimized is right around this like 3.5-ish number. And if we compare that to the projected Bellman error, it's pretty close to it. And then if I add the Bellman error, right, this green curve, it's yet further away, and then this other one is yet even further away. So, you know, on this diagram, it doesn't show exactly how far away each point is, but at least for this example, I have created, no matter what you do with the C value, you get this point of minimum Bellman error and minimum TD error to be farther away from the optimum than the projected Bellman error. And I don't know if I mentioned this already, but another nice thing about the projected Bellman error is, unlike these others, there's actually a point where it is uniquely 0 as opposed to being minimized. So that's another nice property, or at least another, I mean, we always know that we can make it 0, and it turns out that it corresponds to a good objective to strive for. Whereas these other things end up, not having any clear reason to use. The other, sorry, this is just a similar diagram that shows, I make this 0.8. This diagram is actually just showing the point that minimizes all of the errors for each thing. So, right, this, again, this orange line is the point of all the approximation functions. And then this point represents the minimum value error, and this point represents the TD fixed point. And actually, the Bellman error point isn't even on this chart. I have to make this higher to see it. Here, I'll make it a little less bad. But, right, as I keep making this linear constant smaller, this purple point is the point that minimizes the Bellman error. And you can see eventually as I make this smaller, this is going to go negative again and go outside of the graph because, there's no reason for it to be negative, but that should already be a hint that there's something wrong with using this objective, that you get a problem where the only rewards that exist are positive, and yet you get a solution where, W is negative. And then wait, I have one. Oh yeah. So the other thing, this is the thing that isn't shown on this chart, but this is the problem I was showing, and this doesn't have the approximation function on it. But what this is showing is just the process which is sort of sketched out here, which is that, we start out with some point, like here, this starting point is just, it could be anything in the plane, right? Because this whole plane represents the space of all value functions. And then all of these different points are just showing, if you keep applying the Bellman operator, right, you eventually arrive at the true value function here.
So this is the 2D projection on that diagram for the linear value function geometry. Am I correct about that? Between as it's going
So
between
this
value,
well, remember,
W.
well, no, okay, so yeah, so because I've simplified this diagram, so now instead of being in 3D, it is 2D. So no, this would be the analog of this part of the diagram where it goes outside of the plane and arrives at the true point. But because this is right, I'm doing a version of this problem. Now, right, the approximation function is a line. The true value function is the whole plane. And then up here, if you have this point of minimum value error, right, and you apply the Bellman operator, it takes you outside. Instead of outside of the plane, it takes you outside of this line. And this is, the point, the true value function. And here, this one, if you weren't constrained by the approximation, in this case, you can, just move anywhere you want in the plane. Kind of like here, you can move anywhere you want in the 3D space. But right, for this problem, there were 3 states and 2 parameters. And here I'm doing it with 2 states and 1 parameter. Yeah, but I think it is, well, if you go back to this diagram here, but the analog here is, right, like this diagram here is sort of equivalent to this whole diagram, but squashing, the 3D space into a 2D space. It's a little easier to see like this. Yeah, because I think if you did this in 3D, it would be very hard to see what is happening. But yeah, so here the space of all value functions is 3-dimensional. Here the space of all value functions is 2-dimensional. The space of all approximations is 1-dimensional. So here there was a plane slicing through the 3D space. Here there is a line slicing through the 2D space.
Oh, okay, that makes more sense then.
Yeah, so okay, let me see what I want to do next here. But does it make I mean I haven't done the other examples yet, but I mean, even without like additional like derivations, it should already point that there's something wrong with using the Bellman error. If, in fact, the minimum Bellman error would have negative values. All right. Does that at least make sense? Right, this right? Because this problem I set up, right, like there's no negative rewards in this problem. But there's these other examples in the book that show that, yeah, the Bellman error actually gives you strange answers. And remember, like the Bellman error is appropriate to use in the tabular case because, right, when it converges, it becomes zero, which is the whole reason we were using it. It's just that calculating the Bellman error for an approximate value function and then trying to minimize that doesn't actually do what we are trying to do. I mean, it might, the point, like, it seems like it could be a reasonable idea, but, you know, like the fact that the true value function has zero Bellman error doesn't mean that we should strive to minimize it for the approximate value function. But what is a good idea here is to minimize the projected Bellman error because that ends up being the same as the TD fixed point. And in this case, the projection operator is actually easy to figure out, but because, you know, just for any point here, we just need to find the point on this line where the vector connecting them is perpendicular to the approximation line. I think I do. Yeah, and here this is showing algebraically where the point that minimizes the value error is. Also, the way this problem is set up, because I'm using this example, this one, both states are visited an equal percentage of the time. So all the distances in the diagram here, like, are actually the true distance because, like technically you should weight the distance operator by the probability of each state, but the probability weight of each state is actually equal the way I've set up this problem. So you can see, like, geometrically on the diagram what all of the values should be. But, you know, for this problem, again, if you want to calculate the value error, this is just the definition of the value error. And here I've just replaced V1 and V2 with what I computed as the true values earlier using the Bellman equations. And then you can then, you know, take the derivative with respect to W and see where that is minimized. And then this is the value you get where it's minimized. But you can see it is like some complicated function of both C and gamma. And in the extreme case where you make gamma 0, then this is just 2C over 1 plus C squared. But then, so, you know, I already showed it on the diagram, but this is just showing it. If you take this simple problem, this is what, if you write out all of the errors, this is what they look like. So the value error, right, is like each state value, and that's equivalent to this distance here, right? Like that written out is just exactly what the distance of this orange line is, right? Because this is the approximation point, and this is the true value function. So these are all like, all these errors take the form of like a distance metric to a vector. Right, so here's the distance to the true value. Now the Bellman error is different because here we are doing the distance to the Bellman operator applied to the starting value. Right, so here, like, the starting value is W and CW, and then these other two terms are the Bellman operator, which in this diagram is just like this point. So we start here, and then we have this point, and then the Bellman error is the distance from here to here. But if you then, you know, you can then do algebra and compute the derivative of this with respect to W, and you end up getting that the value of W is this, right? This is clearly a different expression than this. I also had this chart up here that showed, right, this is using those equations below, but this is showing the error as a function of W for all of these different metrics. And then, yeah, and then there's this other error which is talked about in this section of the book, which is even different from the Bellman error. This is, I think, oh, sorry, this time at the projected. Oh yeah, here. So I also have here algebraically the projected Bellman error. This, like in general, the projection, there's this comment in the book about how you evaluate the projection matrix, which is dependent on the feature vectors. But in the simplified case of just the 2D geometry that I have, it's pretty easy to calculate what the projection operator is. Because, right, we have some point in the 2D space, V1 and V2, and then we just want to know, like, if we select a point on the line, what is the distance between that point and the true value? And the point on the line is W and CW. So this expression is just the distance between the two. And to see what the projection operator is, we just want to minimize this distance. So you can just, taking this derivative is pretty straightforward. And then you end up with this expression for the projection operator. So this is saying, this is the point, this is the value of W, which minimizes the distance to any, true value, which is, outside of that, the approximation line. But then you could do the same thing, to calculate the projected Bellman error, which is, it's more algebra, but the way this works is, we start out like this point here in the 2D space is what happens when you start with a point W and CW and you apply the Bellman operator to it. So we get this new point, and right, this is like the V1 of the new point, and this is V2. And then we can use this equation to figure out the W that minimizes that. Right, and then the projected Bellman error is the distance between this updated W and the one that we started with along that line. But then, if you actually then calculate the derivative of this with respect to W, then you get another distinct point that minimizes the projected Bellman error here. The mean squared TD error is what is considered in the book here as something instead of the Bellman error. And what it is that here, if you distinguish the two, it's kind of subtle, but with the Bellman error, if you imagine like this expression, you have to imagine this being plugged in here, but we have this expected value of the TD error, and then we have this distance metric on it to minimize it. With this TD, mean square TD error, we consider each TD error separately, and this squaring part is occurring inside of the expected value instead of outside of it. So for the Bellman error, the expression would look almost exactly the same, except, we take the expected value of the TD error first and then square it. But I tried to show it in this diagram up here, but these two black lines, remember, we had this problem here where we had like each state has two different transitions that can occur, right? So for state one, and the probability is split in half. Now, what these two black lines show is that corresponds to two different TD targets per state, which are averaged up. And right, this is the distance to each TD target. And if you look at these two vectors, the Bellman error or to reach this point, the Bellman operator, it should be equivalent to adding up these two vectors, although I think it doesn't look like it because I think this, I don't know if these are exact squares. This might have gotten a little skewed the way the chart is shown, but the two TD error vectors here should add up to equal the Bellman error vector. Now, when we minimize the Bellman error, we put these two TD errors together because we have like the expected value of the TD error, and then we compute the distance on that. The mean square TD error, which is computed here, is considering all of these separately, like the two different targets. And instead of figuring out what the expected error vector is and then getting the distance of that, instead it computes the distance of each of these separately. And the minimum value is the one that actually minimizes the sum in this case of both of these lines, which again, like, this only differs from the Bellman error because the problem is stochastic because there's two different things. Obviously, if there was only one TD target, in which would be the case if the problem was deterministic, then this Bellman error vector would just be the same as the TD error vector because there'd only be one of them. But the difference here is, calculating the distance before we actually combine the TD errors. But, if you say that you want to minimize this, you can then derive what the weight update should be. And that's what's being shown in this section, is there's this weight update, and it looks very similar to the semi-gradient TD method that we had earlier, which is this part of the equation. But there's this additional term here, and that is the difference, is this additional term. But we also have this expression for the TD error itself. So either this is how you would calculate it with a stochastic approach, and then this is actually what the objective is that we're minimizing. In this example, actually, you can solve this example by just actually directly writing down the TD error and minimizing it. But I think, well, maybe I'll just go over this example and then stop for now, and then we can decide if we want to finish the rest of this chapter or move on, because yeah, the examples do get pretty technical. But here, I'll at least try to go over this example. Oh, okay. Sorry, I actually have have yet more charts for this other 2D example I have. Just probably to remind myself what this chart even is. Okay, we can look at that later. Let's see, is this the A? So I believe, okay. Okay, so this example on it is a pretty simple problem, but you can actually see what solution you get with all the different methods with this example. So you start in a state A, and the probability is split, and you can either transition to B or C, but B just always transitions to a terminal state with a reward of 1, and C transitions to a terminal state with a reward of 0. So you can just see what the solution is to this problem without even calculating anything, right? Because B obviously has a value of 1 because it's a deterministic transition, and the terminal state has a value of 0. C has a value of 0. A, the value of A is just should be the average between the value of B and C, which would just be 1/2. So it seems like what the solution should be is the value of A is 1/2, B is 1, C is 0. And actually, if you write down regardless, or that's true if gamma is 1. So we'll just consider cases where gamma is 1. This is an episodic problem. And, this is very simply what the Bellman equations are. And this is just what I said. Okay, so these are the true values. Then you can also consider, we did the semi-gradient TD method before. This is an exact solution. And here, even though we're talking about approximation, we're considering here these approximation techniques, but where we have a different, right, there's WA, WB, and WC. So I'm turning this into a tabular problem, which means that the TD fixed point should give us the exact solution, because if an exact solution is possible, we can take the value error to 0, and the TD fixed point should also have 0 value error. So this is showing each of the weight updates for the semi-gradient TD learning that we had before. And in this case, there's a separate, this is just a tabular problem. So this expression in the parentheses for each is just the TD delta, right? So this is for WA. It's saying that, we have a reward of 0 plus 1/2 times the value estimate we end up at, B and C, minus the starting value. And then for each of these, right, we have the weight minus just the reward you get. Okay, so to find the TD fixed point, we want to know what values of W, A, B, and C do we need for the update to be 0. So these are the easiest to see, right? You can see for this update to be 0, it's pretty simple. We just make WC 0. For this update to be 0, we just make WB 1. And then the only thing left is this one, right? But we already had B and C. So, right, WA just has to be 1/2 because we already have value B of 0. And this, again, is the exact solution that we had before. Okay, so far, so good. Everything is exact. Now, we can look at, right, this definition of the TD error that was, or the mean squared TD error, which was written down. But right now, for this, we actually need to consider all of the transitions, and now there are 4 of them, right, that occur. Turns out they all occur with equal probability. So, right, and the reason why they occur with equal probability is that we start out in state A, right, and then the probability is split between B and C. So clearly A is visited twice as often as B and C, but then there's 2 transitions from it. So, right, this double visit probability is split in half between these 2. So what I've written down here is, right, these are all of the terms of the TD error, which is, right, this delta squared. And there's 4 of them for all of the transitions. So the first one, right, is the WB minus WA. So that's the error for the transition from A to B. This is the error for the transition from A to C. And then this is the one for exiting B and the one for exiting C. Okay, so you square, right, and here we're squaring all of these. And you can do some algebra. And then you can differentiate with respect to A, B, and C. And you get these 3 equations. And then to minimize this, right, all of the terms of the gradient should be 0 at the minimum. So that's what you do here, right? We have 3 equations and 3 unknowns. And then right here we have an expression for B in terms of A, for C in terms of A. You can plug this in to the first equation. And when we get done with everything, we end up solving this and we get WA is 1/2, which matches the solution we had before. Fine. So WA is 1/2. But then, right, we have these other equations for WB, right? So we have WB is 1 plus WA over 2. So that's 1 plus 1/2 over 2 is 3/4. And WC is just WA over 2. and that's 1/4. So apparently our solution that we found minimizing this error is WA is 1/2, WB is 3/4, and WC is 1/4. Instead of WB being 1, right, so this is 1/4 less, and WC being 0, 1/4 more. So this is a problem, right, where like I have a weight for each state. So an exact solution is possible. But if we try to minimize this error, we end up finding a different solution. But I the idea is that whatever approximation method we have, we would at least hope that if an exact solution exists within the parameter space, we could find it, right? Because like an exact solution will bring the value error to 0, and then we already know the TD fixed point will be 0. But this other objective, I mean, all it takes is a single example. Like there could be examples, that there will be example problems where it will find the exact solution. But this is an example, which isn't very complicated, where it doesn't find the exact solution. And that already is a troubling sign that this objective doesn't make a lot of sense. What is strange in this, there's a statement in this chapter that, right, it's in this diagram, that the point at which the projected Bellman error is 0 is the TD fixed point. And we already know the TD fixed point has good properties with the value error. So therefore, the projected Bellman error is a reasonable objective. Now, I've already shown this one, like already there's a major problem with it because of this example. There's another, we'll see the next example, that there is similar problems with the Bellman error. What isn't shown directly in the book is like a proof that if you have this Bellman operator and you do the projection, that you end up getting like the same update as the TD fixed point. Because remember, like the TD fixed point we found by doing the semi-gradient method. So like if we try to apply the gradient method on the value error with bootstrapping, that wasn't a real gradient method, but it was actually converging to a different point. But now it turns out that that point is the point of a true gradient method. It's not the gradient method of the value error with bootstrapping. It's a gradient method of the projected Bellman error. But I don't, like in my notes for these like specific examples, you can show that the projected Bellman like update is the same as the TD0 update with some learning rate. But that's not a general proof. That's just showing for a specific example. And of course, like the point is that these other objectives, like this one, don't have any clear relationship to the value error, which is why they are bad ideas. But even without that argument, just this example already shows that in the case of having an exact solution possible, we don't even find it using this objective. But yeah, I think that's, I don't know. I don't really want to go on because I feel like it's already a lot of technical stuff, and I should maybe
Well, I guess, for the tabular method, the difference between the two optimization functions for the value error and the TDE solution makes sense, since essentially it's just taking, the partial derivatives and then finding the solution to it. So, and then, how the the fixed point, because the fixed point is the actual tabular solution, and how it converges into the statuses of the WA, WB, and WC makes sense compared to the solutions for the TDE solution. Doesn't make really much sense.
Yeah, well, this solution is, well, first of all, it's wrong, but in terms of it not making sense, I guess what you're more saying is that conceptually what shouldn't make sense here is the objective doesn't make sense. But the point of this example is that maybe this objective looks like it makes some sense, like it looks like a reasonable thing to minimize, but then obviously like you get the wrong answer. You can see you get the wrong answer from doing the algebra, but actually seeing why the objective doesn't make sense might be a little more subtle or not as clear. This chapter and in general, like when this value error was introduced in the first place, it was already sort of stated that like this is somewhat arbitrary. Like it just seems like a good idea to try to minimize the distance to the true values. And right, this doesn't depend on like if you're actually using this like where it doesn't depend on the approximation, logically, yeah, like we want our approximate solution to be as close to the true values as possible. That was like the original concept behind approximation. Now, in this chapter, like all these other things are introduced with the idea of showing that none of them really make sense, although they did make sense. Like the analogy to the tabular case was that in the tabular case, we are also trying to make the value error, zero, right? Because we're trying to find all the true values. The value error is zero, but in the tabular case, all of these errors would be zero. Actually, except for this one. This is the only error which actually even fails in the tabular case. But in the tabular case, like, right, if we actually have the true values, we already know that the Bellman, like, right, the Bellman error or this Bellman operator, right here, this is the statement that at the true value function, the Bellman operator leaves the values unchanged. So the Bellman error is zero. But again, the problem with approximation is that we cannot make either the value error zero or the Bellman error zero. But, then the question is, what do we want to actually minimize? There is, however, one thing that we can make zero in the case of approximation. But, it was shown here, right? But that the thing we can make zero is the projected Bellman error, which is this. I'm sorry, this is if I change the way, right? And this is like, in terms of doing the learning process, right? It's like you have this approximation, you see, oh, this is the projected Bellman error, right? It's to the left here. So then you update the weights in the direction of minimizing the projected Bellman error. And then, eventually you reach a point, right, where this dashed line is perpendicular. And this is the point, and it's shown here, where this projected Bellman error is zero. So just intuitively, that, in tabular learning, the goal was to make all the values exactly correct. So there's zero error. In approximation, especially if we don't have an episodic problem, so we can't even like collect estimates of this, we can only do it with bootstrapping. The best we can sort of hope for is to find the point where the projected Bellman error is zero, which it turns out the semi-gradient methods we already found did that. Now, the final part of this chapter, after a couple other examples, is an algorithm which actually directly tries to minimize the projected Bellman error. Or it's, yeah, like this thing, right, which is like the Bellman error projected into the space of approximations. And what should be the case is that, now the whole point of doing this is for the off policy case, because right in the on policy case, we already have an algorithm that minimizes the projected Bellman error. That was just all the semi-gradient TD methods. But again, those don't work in general in the off policy case because they depend on visiting the states in the correct frequency for the behavior policy, or for the target policy. But if you look at the algorithm that just directly minimizes the projected Bellman error, and you do it in the on policy case, right, it should be equivalent to the semi-gradient TD method because it was already proven that, I mean, unless, I guess it could be different in that it converges faster, but it was already shown that both of those methods converge to the TD fixed point, which is the point that we are, trying to reach for these, approximation problems. I mean, we wouldn't need to bother with the TD fixed point if we could, actually estimate the true value function, right? But we can only estimate the true value function like for real in an episodic problem where we can just like do a Monte Carlo sample of the discounted reward. And in, a problem like I was showing like this, right, you can't actually sample the true values because it's a continuing problem. So you have to take the discounted sum out to infinity. And which is why you have to rely on the bootstrapping. But again, the bootstrapping forces us to consider this alternative objective, which luckily is, at least for all the examples that you can sort of write down, you would find that this point of minimizing the projected Bellman error would be the closest thing you could actually compute to the minimum value error, which is the whole reason why we use it. But, I think all of the different objectives in this chapter are not that straightforward to understand. I was hoping that, I think this 2D visual diagram is very helpful at seeing everything, but it probably requires looking at it for a while yourself and reading how it works to get a sense of everything. But it's just trying to put on the plane all these different, terms that exist in the different errors. And the concept, again, is like all these errors with this, squared, all these square terms. The reason why all these terms are squared is because they are calculating a distance or, the length of a vector. And of course, when we calculate the length of a vector, we have to, right, square all the different components, take the squared sum, just following the Pythagorean theorem.
Well, if you want to, compute a Euclidean distance, then that would be, a square. But there's a bunch of different distance metrics.
Yeah, but for like the thing we said we were trying to minimize in this case, like this is the Euclidean distance with, it is weighted differently for each dimension where each state is a different dimension. But yeah, this is this Euclidean distance metric. But yeah, of course, like this is a somewhat arbitrary choice. Like we could have picked a different distance. If you use this objective, though, at least we have some convergence guarantees to getting close to it. You would have to prove with, if you pick some other metric, that, you could actually converge to something close to it. And in this case, we also wanted to show that the semi-gradient method also could converge to something close to it. But yeah, certainly these other metrics, yeah, do not, like this one especially. I mean, this is the worst one by far because this one doesn't even converge to the correct values for the tabular problem. So, this is just so again, like this chapter is a little confusing because it sort of proposes things that are actually bad ideas, but seem like, oh yeah, why don't we just try that? And then demonstrate why they are bad ideas. But it does sort of make it a little confusing if you're just trying to figure out what the best thing to do is. But I think, they do provide a lot of insight into what can go wrong. It's hard to get that insight without looking at it for a long time on your own. But I think, if you read these notes or look at the code, I hope the 2D example makes things a little more clear. But I think so. I don't know. I guess I don't know. Next time, I'm not sure. I mean, I feel like I kind of would like to finish the rest of the examples and then go over these gradient TD methods. But yeah, it is going to be then another meeting of somewhat more technical math and some of these thought experiments with different examples. But at least it'll give me a chance to finish the notes and hopefully make everything written up as clear as possible.